Hello everyone, I hope you're well. In this video, I'm going to be giving you the solution to an interview question which I myself was asked when I applied to study maths at Cambridge in December 2021. So you might look at this question, which is to sketch the graph of y squared equals x arctan 1 over x and think, this is completely ridiculous. How would anyone know how to sketch something like this? And actually, that is my exact thoughts. Those were my exact thoughts when I was in the interview. But I think this really captures the spirit of Oxbridge interview questions because they will always be something that's hard and something that you haven't seen at school. But what they're looking for is not how fast can I get the answer, and as if it were an A-level exam where they're just giving you ticks for every right thing that you say. But instead, they're just generally curious about how you respond to difficult and unfamiliar situations. They're just curious about your thought process essentially. So you can actually get a lot of credit for just really communicating your thoughts clearly, even if you say something that's completely nonsense, because they want to see that even if you don't know the answer immediately, that you're essentially teachable. In particular, I'd say that they're looking for how well suited you would be to the Oxbridge supervision and tutorial system, where you have, say, a small 2-on-1 or 1-on-1 class with, say, 2 students and 1 academic. So really, the interview intends to simulate a supervision. Okay, so with this in mind, I'd like you to take about 5-10 minutes to have a go at this on your own. And remember, don't be disheartened if you don't get the answer, but at least see how much you can brainstorm in the time allowed. Okay, so if you've kept watching, then that means that you've had a go and you'd like to now hear about the solution. So I think before we get started with this particular graph, I want to give you some general pointers about how you might approach curve sketching questions. So I would stress that this is nothing like at school where you're given quite an easy graph, like say y equals x squared plus 6x plus 9, and you basically just plug in values of x, then you get the corresponding values of y, and then you just plot them on a graph. This is nothing like that because it's going to be very impractical to plot basically every point. You don't even know what arctan of fifth is unless you had a calculator. So, and by the way, you aren't allowed to use calculators in the interview. So instead, what you should be trying to do is just giving general qualitative observations about the shape of the graph at various points. So I can give you a few tactics that you might use. The first is, and this might be in contradiction to what I just said, but what happens to the graph at 0 and 1? So, what's y evaluated at 0 and at 1? And that's because, okay, you might not know how to evaluate the graph at x equals 5, but usually at 0, it would be quite a nice value. Usually it goes through the origin, or it'll go through 0, 1, or there'll be an asymptote at the origin, at x equals 0, that is, and something like that. So, you can usually get a lot of information about the graph just by plugging in 0, or maybe 1, depending on what graph it is. And then beyond that, I'd say those are the only points you should really plot, unless there's like a really obvious point based off of the structure of the graph that you might try. But then, you want to be looking at, say, symmetry. So by this, I mean, is the graph symmetrical about some axis, like say the x-axis or the y-axis, or indeed any other line? Because if it is, then that simplifies the problem quite a bit, because you only have to consider, say, one small region, and then you can do some reflections to get to the final answer. And then next, I would say, try to look at, large and small values. So you won't be able to do any precise calculations here, but you could answer something like, what happens to this graph near infinity or minus infinity? And usually your answer will be something like, oh, it's quite large, or it's quite small, or it's approximately this value. And then next, I would say you want to consider maybe, is there a maximum or minimum that the graph takes? So again, what you probably shouldn't do is to differentiate and then set the derivative equal to 0, because that might be quite tricky for quite a lot of graphs. But you might be able to use your mathematical intuition to maybe suggest what a maximum or minimum might be. And then I would say next you want to consider, and I'd say I put this maybe here, you might consider, is there like a simpler graph that you can consider? So, you might not know what y squared equals x arctan 1 over x looks like, but you might know, say, what y equals arctan 1 over x looks like. And then you can sort of use the same intuition that you've built from doing that problem to answer the original problem. And then finally, I'd say there might be some approximations that you can make at various points. So I think, for example, you know that if you had, say, let's say x to the 4 plus 1 over x squared plus 1. Let's say that this was the graph. So I have no idea what this graph looks like. I just made it up on the spot. But I can say that if x is really small, then this is approximately 0, and this is also approximately 0. So this graph is approximately 1. when x is small, basically when x approaches 0, let's say. So that can be sort of helpful in some cases. Okay, so now that I've given you these hints, you might like to spend a bit more time thinking about it. Maybe you can, if you've not considered one of these points, you might like to do that. And then I'd say come back in about 5 minutes and let's discuss the solution. Okay, so if you've kept watching, that means we're now going to go through the solution. So, okay, we want to sketch the graph of y squared equals x arctan 1 over x. And the first observation, it's x arctan 1 over x. And the first observation to be made is that there's a y squared here. So what does that mean? Well, that means, let's say the graph went through, for example, the point 1, 2. I don't know if it does, that was just an example. Then it's also going to go through 1 minus 2, because if, y equals 2, 2 squared is 4, but also minus 2 squared is 4 as well. So that means that there's going to be some symmetry by the x-axis, isn't there? Because any point that that has a positive value of y, there's a corresponding point with a negative value for y. And then also, this is slightly harder to spot, but I do think it does help the problem quite a lot, is there's also going to be symmetry about the y-axis as well. And that's because if I plugged in minus x, I get minus x times arctan of minus 1 over x. And now, okay, you should know by considering the graph of tan x, or maybe you just knew this as a fact, that tan of minus x equals minus tan of x. So you can see here that now, if I were to take the arctan of both sides, I'm going to get that we have arctan of minus x is minus arctan of x. And you also know that this is true because arctan's an angle. So if you basically were to tan the negative of that angle, you get minus the final result. So you know that if you tan arctan of x, you get x. So if you tan minus arctan of x, it should make sense that you'd get minus x because tan minus x equals minus tan x. So with that in mind, you know that, okay, this is minus x times minus arctan of 1 over x. And then, so you see the minuses cancel. So really, you get the same result if you plug in minus x. So we've got symmetry about the x-axis and the y-axis, which is really useful because that means now we only need to consider the top right quadrant. And then we could just reflect across the x-axis and the y-axis to get our final answer. So why don't I scroll down and I'm going to draw the positive y-axis and the positive x-axis. So the next step here is to consider maybe, what about, so x equals 1 is not so useful because we're going to have to square root pi by 4, which is a bit cumbersome and it doesn't really tell us anything. But maybe we can consider what happens to the graph at 0. So if you have y squared equals. So we aren't going to be able to find the exact value because we can't divide by 0, but we can take a limit. So let's consider what's the limit as x approaches 0 of x arctan 1 over x. Well, as for the x, that's fine because you know that this term here is going to be equal to 0. But, and by the way, I'm just going to, you should suspend your disbelief about really about how rigorous what I'm about to do is, because it's an interview and it's also a curve sketching question, so they're not really looking for a lot of rigor, just general intuition. So in this case, I would say, well, okay, so what we're doing here is considering as x goes to 0. So 1 over x is going to be really large. It's going to approach infinity. So let's say, what happens to arctan when you're at, say, 1 million or 1 billion? What's the arctan of 1 million or just a very large number? And if you consider the graph of arctan of x, you should know from school that it looks something like this. And so really there are asymptotes at pi by 2 and minus pi by 2. So we know that as x approaches infinity, arctan of x approaches pi by 2. So as x approaches 0, arctan of 1 over x should also approach pi by 2. So this is going to be basically 0 times pi by 2, which is 0. So the graph goes through the origin, which I think is massively helpful because now we know sort of basically that there's not an asymptote. It doesn't behave horribly. It's got quite a nice value and we can sort of work from there. So next I'd say, well, okay, we've sort of considered 0 and 1. Why don't we now consider like large values? So what's the behavior of this graph as x gets really large? Because we've now considered when it's really small. So, okay, so we want now to take, if I just scroll down a bit, the limit as x approaches infinity of our graph of x arctan 1 over x. Well, this is going to be a bit awkward to do because if we have an infinity here, and we have like a 1 over infinity, which is, we're going to say 0, so arctan of 0. So basically we have like a kind of 0 times infinity thing here, which is a bit awkward to deal with. So we're going to have to think about another way we can evaluate this limit other than just directly doing it. Well, okay, we got arctan, so we're thinking about trig. What sort of limits do you know in the topic of trigonometry? Well, there's the small angle approximations, isn't there? So that might be useful in this case. And you can see why it might be, because if 1 over x, so if x goes to infinity, then 1 over x is really small. So actually, we are going to be able to use a small angle approximation, I think. And let's think, what are we going to do? So if 1 over x is small, what's like arctan of 1 over x? Well, we know that, so tan of 1 over x is going to be approximately 1 over x, because that's the small angle approximation of tan. So if I just arctan both sides, I get 1 over x is approximately arctan of 1 over x. So, okay, then we know now as x approaches infinity, this is going to be basically x times 1 over x, which is 1. So that means, to recap, that as x approaches infinity, y squared approaches 1. So y approaches 1, because we're just considering the top right quadrant. So in particular, that means we have a horizontal asymptote at y equals 1. So at this stage, we're almost done, because we know that at x equals 0, we're at the origin, and then as x goes to infinity, we go to 1. So basically, we're going to have to climb from 0 to 1 in some way. And at this stage, what I did was I had a bit of a concern, which I asked the interviewer, which is that, well, you don't really know whether it goes up in like a concave or a convex manner. So you don't know if it kind of goes up like this or goes up like this. And the interviewer actually said that it doesn't really matter. You can just draw whatever shape you want, because you're just looking for general intuition rather than specific ideas. And anyway, in order to answer the question about convexity or concavity, usually you might have to consider something horrible like the second derivative, which you won't have time to do in the interview, where they're just looking for you to make approximations. So I said, well, okay, it makes the most sense for it to go up like this, because if it goes up the other direction, then it's going to be a bit awkward for it to like take forever to go up to 1, unless it did it in like a really, really like that. So I think basically this makes more sense. And the interviewer said that was correct. That was the shape. So remember, we're not done yet, because we still have to reflect across the other two axes. So let me just quickly do that. So we have this, and then we're going to reflect. So we have this shape, and then this, and then this. So I'm just going to quickly draw on the asymptote at 1 and at -1. Okay, nice. So this is what the graph looks like. And at this stage, the interviewer then asked me a follow-up question, which I'm going to give you a bit of background to, and then I'm just going to get you to go off and think about this. So, with some graphs, like let's take y equals square root of x. As we approach the origin, it kind of looks a bit like this, doesn't it? So it kind of approaches the y-axis from like vertically. So it kind of, there's a sort of vertical shape of the graph near the origin. And then, so if I say this is y equals root of x. And then, okay, then there are graphs like y equals x squared, where it kind of approaches it horizontally. So like this, the curve looks quite flat near the origin. So this is y equals x squared. And then finally, there's sort of something in the middle where if you considered y equals x, well, it approaches it kind of obliquely like this. It's just from the side. So the question I was asked was like, what happens in the case of this graph? Because you see, what we've drawn actually doesn't really make it clear which shape it is, because we were quite vague about most of the graph apart from at the extremes. So the interviewer then said, how could you investigate something like this? And the key here is we are actually going to have to do a bit of differentiation. So if we have y squared equals x arctan 1 over x, we want to basically compare the derivative at small values with the derivative to either one of these three graphs. And we want to see like which one is it going to be. Because we know that if we get like a very big number, it's going to look maybe something like y equals root x. If we get a small number, it's going to look like y equals x squared. And then if we get like something quite average, like approximately 1, it's going to look like y equals x. So, okay, we're going to have to do this by implicit differentiation. So if we differentiate this, you're going to get 2y times dy by dx. And then this is going to be awkward. We're going to have to use the product rule. So if I will differentiate this and leave this alone, so we get arctan of 1 over x. plus, okay, and now we're going to have to use a chain rule here. So the derivative of arctan of x, you should know, is 1 over 1 plus x squared. So it's going to be 1 over 1 plus 1 over x squared, and then times by the derivative of 1 over x, which is minus 1 over x squared. So this is going to be arctan 1 over x plus, and then, okay, so I'm now going to have to, so this will be a minus, and it's going to be x over, well, it will be 1 plus x squared here, because it's going to be basically x squared times 1 plus 1 over x squared times x squared. Okay, and now we're going to have to think, okay, x is small, so we know that what we end up getting is something like, well, arctan of a big number, which is pi by 2. And then as for this, well, we can do a quick approximation. So this is going to be, if I divide the numerator and denominator by x, I get 1 over x plus x. So if I approach 0, well, it's going to be 1 over 0 and then 1 over something really big, which, so that's going to be like, say, infinity, and 1 over infinity is 0. So you get basically approximately pi over 2. And then now we can say that, well, we're now going to have to maybe think about y. So if we think, what's the value of y, for small. So I was saying, what's the value for y, like for small x? Well, we know that it kind of approaches 0. So we're here going to have to say something like dy by dx is going to be pi over 4. Wait, let me see if I got this right. Yeah, pi over 4y. But, if x approaches 0, so if y approaches 0, then we have like 1 over y is really big. So this is going to basically explode. Basically, it's just going to explode off to infinity. So we know that then if basically the gradient's really large near the origin. So we can say that it's going to behave something like root of x. And that also does make sense, because if you look at this graph, it actually does look a little bit like the square root of x if I were to reflect it across both axes. That's just a sort of general observation you might have made when you did the curve sketch. Okay, so that's everything I want to talk about with this question. So thank you for watching, and I hope you found this useful. I would say that you want to definitely practice a lot of curve sketching questions if you're applying for a STEM subject. And remember the advice which I told you at the start, which is to focus on general ideas rather than specific calculations. And yeah, I would say you can, at the end, verify your results with Desmos. You can ask your friends to make up graphs, for example, or you can find a lot of them online. I'd say definitely for me that I overlooked curve sketching until about a month before the interview. And then it ended up basically saving my application because, I was asked 2 questions in my interview. This was one of them. So if I had not done well on this, then I definitely wouldn't have got in. So I'd say curve sketching is absolutely vital. Thank you very much.